Hello, my name is Ricardo Max, and I'll present you findings from a new behavioral methodology called the Mutations paradigm, whose results contradict traditional assumptions about visual selection. The main question addressed here is when and how does the flanker interference effect builds up? Specifically, our findings suggest that flanker effects reflect the initial time necessary to suppress distractors rather than post-perceptual response competitions, which have been traditionally assumed to be caused by inefficient operation of attentional mechanisms. So for the last 40 years, the flanker paradigm has become the golden standard for research on visual spatial selection. In a typical flanker task, participants respond as fast as possible to a central target that has two alternative identities and is presented together with flanking distractors, which can be either incongruent or neutral to a given target. So typically, when a target is flanked by incongruent distractors, whose identity is the alternative target, that is, the incorrect response, responses are slower and less accurate than when the same target is flanked by neutral distractors, whose identity is not associated with neither motor response. So the flanker effect has been defined as a performance interference by incongruent distractors. Well, many explanations have been proposed for the flanker effect. Maybe because the area usually is too small, or because we tend to chunk adjacent stimuli into one object, or because resources slip towards distractors or leak towards them. But irrespective of why the system fails to ignore distractors, all theories of attention have agreed on two basic assumptions. First, that attentional mechanisms are inherently unfit to filter out distractors within a typical flanker configuration. And second, that the flanker effect, which is slower responses for incongruent displays, is a consequence of a post-perceptual time-consuming response competition. That is, in an incongruent display, while the target identity activates the correct motor response, the incongruent identity of the distractors simultaneously activates the incorrect motor response, which end up competing with the correct response. In a neutral display, on the other hand, the neutral identities of the distractors do not activate any response. So according to the response competition hypothesis, responses to incongruent displays are slower because the two simultaneously activated motor responses end up competing with each other, which demands additional processing time for the system to suppress the incorrect response in favor of the correct one. And this additional time, has been assumed to cause the flanker effect. Now, the core empirical support for the response competition hypothesis comes from vast electrophysiological evidence showing indeed that incongruent displays evoke simultaneous activations from response preparation stages up to muscular activity in both hands. But what these studies fail to address is the assumption, or maybe the hidden assumption, that the resolution for this competition indeed demands additional time, instead of, for instance, a horse race competition in which the fastest activation wins without interacting with parallel activations. That is, if the flanker effect is caused by a response competition, then we should see a positive correlation between the amount of incorrect response activity and the size of the flanker effect observed. And in fact, Uwe Madler, 2005, using the same electrophysiological measurements mentioned before, found that the magnitude of the response competition did not correlate with, and thus could not account for, the magnitude of the flanker effect observed. So, if not during late post-perceptual stages, then when is the processing of incongruent displays delayed? We address this question by focusing on the initial stages of processing, and we use the Mutations protocol, which provides direct assessments of the initial time window during which the system extracts critical visual information from each presented stimulus. Now, first of all, before I explain the mutations manipulations, I'll mention that we've tried a wide variety of different stimuli and display configurations, and they have all produced the same general results that I'll show you later. So here, in experiment 1, as in all mutation experiments, there were two alternative targets, so there were two types of incongruent displays, and we also had two different types of neutral distractors. So we had 4 types of neutral displays, and you'll soon understand why. On each trial, While the target remained unchanged from onset until response, the identity of both distractors mutated to a different identity once per trial at a random time. And after the mutation, the post-mutation display remained on screen until response. There were three types of mutation trials. Trials that initially presented incongruent distractors that mutated to neutral distractors, vice versa, neutral that mutated to incongruent, and our control trials in which neutral distractors mutated to different neutral distractors. For all these trials, the distractors mutated once, randomly, at 1 out of 8 alternative mutation times, between 16 and 75 milliseconds after onset, in steps of 8.3 milliseconds. For example, here we have an incongruent to neutral trial mutated at 41 milliseconds, so the target never changes. Incongruent distractors were presented during the initial 41 milliseconds, and then they were replaced by neutral distractors that remained until response. Here we have a neutral to incongruent mutation at 25 milliseconds. Again, the target never changes. Neutral distractors presented during the initial 25 milliseconds and then replaced by incongruent distractors that remain for the rest of the presentation. Lastly, in addition to the three types of mutation trials, we also had two types of baseline trials without any mutation that presented either an incongruent or a neutral display from onset until response. Again, throughout each entire presentation, the target never changed, so there was no question about which one was the correct response. So here we have reaction time on the ordinate by the time of mutation on the abscissa. First, these are neutral baseline trials without mutations, followed by neutral to neutral trials mutated at 16, 25, 33, 41, etc. So first of all, we can clearly see that the mutation manipulation itself had no effect whatsoever on performance, so this is a flat line. And now we compare these to the two other types of mutation trials. So the red dot here represents incongruent baseline trials without any mutation, which, compared to the neutral baseline trials, the black dot reveals a straightforward replication of the classic flanker effect. So when incongruent distractors were uninterruptedly presented from onset until response, reaction times were delayed by 37 milliseconds. Now when the same incongruent distractors appeared only 16 milliseconds later and then remained on screen for more than 400 something milliseconds until response, the flanker effect already dropped by 2/3. Again, here we had neutral distractors presented for miser 16 milliseconds, so they were completely subliminal and masked by the incongruent distractors, but now responses were delayed by only 13 milliseconds, still significant, but 1/3 of the delay for when incongruent distractors were presented throughout the entire presentation. When incongruent distractors replaced neutral distractors after 25 milliseconds, the flanker effect dropped to 9 milliseconds, hardly approaching significance. And when incongruent distractors appeared after 33 milliseconds or later, they became completely inconsequential. They were completely ignored. So here neutral distractors were presented for only 33 milliseconds and then replaced backward masked by incongruent distractors that remained on screen for additional 420 milliseconds more or less. So phenomenologically, participants saw only the incongruent distractors, but behaviorally, their responses were fully determined by the subliminal neutral distractors. The middle panel here shows the flanker effect observed for each mutation time, which is the reaction time difference between the red and the black functions on the upper panel. And at the bottom we have the effect size for each of those comparisons. So this gray area is identical to this gray area. A two-phase linear regression of flanker effect by time of mutation revealed a breakpoint at 29 milliseconds after onset, which indicates that the accumulation of information about neutral distractors ended after 29 milliseconds of presentation. Now let's see incongruent to neutral mutations. When incongruent distractors were presented during the initial 16 milliseconds and then replaced by neutral distractors, not much happened, neither at 25 milliseconds. But when incongruent distractors were presented for only 33 milliseconds, responses were already delayed significantly by 17 milliseconds. Again, I remind you that these incongruent distractors were completely masked by the neutral ones. The longer incongruent distractors were presented, the slower the responses, until 75 milliseconds after onset. for which reaction times were identical to those observed on incongruent baseline trials. Not only these two different trial types rendered the exact same reaction times, but they also resulted in equivalent flanker effects, which means that the presentation of incongruent distractors for longer than 75 milliseconds was inconsequential to performance. Which means that the accumulation of visual information about incongruent distractors ended around 75 milliseconds, while for neutral distractors it ended after 29 milliseconds. So in contrast to the conventional assumption that during early processing stages, both neutral and incongruent distractors are processed or inefficiently processed to the same extent, the mutations manipulations reveal a striking 46 milliseconds discrepancy between them. As I mentioned before, we have observed these patterns across a variety of different stimuli and configurations. Neutral distractors were processed within the initial 15 to 30 milliseconds after onset, while incongruent distractors continue to be processed until later than 50 milliseconds. So far we saw what happened to distractors. Now let's see what happens to the target when it's flanked by incongruent or by neutral distractors. This experiment was ran in collaboration with Hailey Lagua, Vince DiLolo, and Tom Spalek in Simon Fraser University in Vancouver. So here we presented the exact same incongruent or neutral displays used in experiment 1, and then we simply masked the display at a random time after onset. We assume that if the masking display is presented while the system is still accumulating critical information about the target, then target identification should be disrupted. But if the masking display appears after the system has already gathered all critical information, then the masking should remain inconsequential. So for both types of trial, incongruent to mask and neutral to mask, the masking display was presented randomly at 1 out of 7 different times between 8 and 92 milliseconds after onset. And now we measured accuracy instead of reaction time. So for the ordinate we have error rates and the time of masking on the abscissa. For neutral displays, the later the mask, the less errors were committed, until a floor level of 4% errors when neutral displays were masked at 75 milliseconds or later than that. We ran a two-phase linear regression, which revealed that after 63 milliseconds, the system finished to accumulate all critical information necessary for optimal identifications of a target that was flanked by neutral distractors. For incongruent displays, on the other hand, the masking continued to disrupt responses until our latest masking time at 92 milliseconds. So we fitted this function, which estimated that a lower asymptote for a baseline error rate of 7.7% errors could not be reached before 104 milliseconds after onset. Now this is an underestimation because the 7.7% baseline was derived from experiment 1, in which participants were instructed to respond as fast as possible, while here they were explicitly instructed to take as long as necessary. In sum, experiment 2 revealed that, while the system needed 63 milliseconds to collect all critical information in order to identify or optimally identify a target that was flanked by neutral distractors, it needed at least 104 milliseconds to identify the exact same target when it was flanked by incongruent distractors. Taking both experiments together, first of all, we can see that after the system ceased to accumulate information about the distractors, it continued to accumulate critical information about the target, both for neutral as well as for incongruent distractors. These allow us to conclude that distractors were actively and selectively suppressed at those times. So contrary to traditional assumptions, not only the system achieved fully efficient suppressions of flanking distractors within the initial few dozen milliseconds of presentation, but also the time course of initial processing was significantly different for neutral and incongruent distractors. Okay, so we can discern between 3 different stages of processing. The first stage is the initial time until distractors were suppressed, followed by an additional perceptual stage during which the system accumulated information exclusively about the target, followed by post-perceptual processing until response, after all information had already been collected, and during which any visual event was inconsequential to performance. Now we can see that the post-perceptual stage was by far the longest one of the three stages. So for incongruent displays, post-perceptual processing was 75% of the entire time taken from stimulus onset until response. For neutral displays, it was 85% of the entire processing. Now, as we saw before, the response competition hypothesis assumes that the flanker effect occurs because post-perceptual processing of incongruent displays takes longer than neutral displays. While here, the post-perceptual processing of incongruent displays was 4 milliseconds faster than neutral displays, and that was an underestimation, as I explained before. The second stage, the exclusive target processing stage for incongruent displays, was also slightly faster than for neutral displays by 5 milliseconds. And the only stage during which incongruent processing was slower than neutral was the initial time until distractors were suppressed, which took almost 3 times longer for incongruent displays than for neutral displays. Which means that this was the only stage during which the flanker effect could have built up. That is, compared to neutral displays, the additional time that was necessary in order to suppress incongruent distractors delayed all subsequent stages until the actual response. Now, why suppressions of incongruent distractors take significantly longer than suppressions of neutral distractors is a different story. We have proposed one possible explanation, which you can find in the link on the bottom of the screen. To conclude, first, in contrary to the response competition hypothesis, according to which the flanker effect builds up only at the last stage just before response execution, we conclude that the flanker effects observed here reflected the initial time necessary to suppress distractors. Second, in contrast to the traditional assumption that attentional mechanisms are inherently incapable to filter out distractors within a typical flanker display, we saw that the system achieved fully efficient suppressions of flanking distractors within the initial few dozen milliseconds of presentation. Thank you very much.